And now we're going to start looking at expected value. Expected values are a way to use probabilities to try to figure out what's going to happen in the long run in a certain situation. Okay, so there's a couple really important things that we need for expected value, and one of them is that the individual outcomes must have a numerical value associated with them. Okay, so a real nice example would be like the dice, rolling a dice, right? You've got numbers 1 through 6. Each outcome has a numerical value. Heads and tails, flipping a coin is not this way because heads and tails are not numerical values. Now you could associate a numerical value like a 0 and a 1 to a head and a tail or something like that. But you have to have some sort of numerical value associated with the outcomes in order to use an expected value or to calculate an expected value. Okay, so just real briefly, the way that you calculate an expected value is you multiply the value of the outcome. That would be like on a die roll, would be like the numbers 1 through 6. The number or the value of the outcome by its probability, and add those products together. Okay, so I'll give you the example with the dice roll. It's a very common example, kind of your basic example. Each of the 6 numbers has a 1/6 chance of being rolled, right? The probability is 1/6. And so you take the outcomes, put them in a column. No, they're 1, 2, 3, 4, 5, and 6, and multiply them by their probabilities. Put those in another column. So each of these has a 1/6 probability. Should have made this table a little bit smaller, a little spread out here, but that's okay. So you get 1/6 probability for each, and then their product in another column. And a lot of times we use tables to organize our thoughts on expected values. That way you can match things up appropriately and you don't miss something. So the product is going to be 1 times 1/6 is 1/6. 2 times 1/6 is 2/6. And I'm going to not reduce the fractions here because in the end I'm going to want to add these together, and I want my common denominator to be there. If I reduce this to 1/3, I have to rebuild everything up with a common denominator at the end, and it's kind of messy. So it's just nice, at least at the beginning here, not to reduce the fractions, but then to reduce it at the end. So 2/6, 3 times 1/6 is 3/6, 4 times 1/6 is 4/6, and so on, 5/6 and 6/6. So these are the products. Now the expected value is then found by adding up these products, right? So add them together, and you get 1 plus 2 is 3, and 3 is 6, and 4 is 10, 15, 21/6. So you get 21/6, and 21/6, if you reduce that, divide them both by 3, that's equivalent to 7/3. I'm sorry, 7/2. And 7/2 is 3.5. Now, there is no die roll that is a 3.5, right? There's 1, 2, 3, 4, 5, 6. But over the long haul, if you were to roll dice over and over and over and over and over again, the long-term average of those rolls will be 3.5, 3.5. So an expected value really gives you kind of an idea of a long-term average. If you were to do this over and over and over and over again, what would you expect to get overall? Okay, now you'll never actually get a 3.5 output, but it's the kind of the average of all the long-term outputs. Another interesting example, if any of you have ever had a friendly wager on a sporting event, a lot of people use for March Madness, the NCAA basketball tournament, or for the Super Bowl, they'll put some money down and have a little competition, friendly competition with some people, on what they think will happen. And so I'll make a game that's kind of like that, where that could happen. Let's say, for instance, you had 10 10 people, you and 9 of your friends got together, and you each put $5 into a pot, and then you know, whether it's for a basketball tournament or a football game or whatever it is, and you try to figure out for the basketball tournament, you try to pick the games or whatever, and then the person with the most right or the most points based upon the rounds and that sort of thing can get part of the pot. And maybe you go with a first and second place, so split it up a little bit. So let's give the scenario here. I'll make it a little bit more formal. Let's say you had 10 friends or 10 people, and each gives $5 to the pot, right? So there's $50 in this pot. So 10 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know. There's 10 people all giving $5. Right, $5 each into this pot of 50. Okay, and then from that, the winner, whoever has the most points or whoever guessed the score the most accurately or whatever, gets let's say first place gets let's go with $35. Now you could split this up, you could divvy it up however you wanted. It would change the expected value, but let's just go with $35. And then second place, let's say you get a second place, $15. That way a couple people get some money back, and everybody else just put in their $5. Okay, and so in the end, you've got $50 coming in, you got $50 coming out. Now, how does this play out in an expected value? Well, you have the outcomes. What are the possible outcomes? Well, the possible outcomes are you could win $35, right? You could be up 35. You could be up 15, so you could make $15. Or you could lose $5, right? If you're put money in and you didn't win, if you were one of the bottom 8 people. So you could lose $5. In the end, there are 2 people who will make this much, and well, actually that's not true. Oh, this is interesting. I just realized this. I did that wrong. Everybody puts $5 in, even the 2 people who won. So if you put $5 in, if you win second place, you put $5 in, and then you win 15. You've really only made 10, right? So this should really be 10. And if you put $5 in and you get first place and you win 35 back, 5 of that is your own money, and so you really only won $30, right? So in the end, one person wins $30, one person wins 10, and 8 people will lose 5. Okay, that's really how it plays out. Okay, so those are the 3 possible actual outcomes in the end. Then the probabilities, I'll just abbreviate. The probabilities are found. I'm just going to assume it's equal probability, equally likely that anybody will win. Okay, so it's a 1/10 probability for each person. So you have a 1/10 probability of getting $30 being first place. You have a 1/10 probability of getting second place. I'm assuming there's no ties, so maybe there's some tiebreakers factored in if there was a tie in some way. And there are 8 people who will miss out and lose $5, right? So 8 out of 10. And so here we can figure out the expected value again by multiplying the corresponding outcome with its probability, and then adding the probability, or adding those products together. All right, so the product, 30 times 1/10 is 30 tenths. Again, I'm not going to reduce the fractions temporarily here, and then we'll reduce it in the end. 10 times 1/10 is 1, or 10 tenths. And 5 times 8 tenths is 40 tenths, right? 5 times, yeah. And so when you add these up, oh, but it's negative. Notice that it's negative here. This is a negative 40. And so when you add those up, 30 plus 10 minus 40 gives you 0 tenths. Interesting. So in the long run, that's $0. So in the long run, the expected value is 0. So it's really just fun and games. The money doesn't matter. If you were to play the same game with the same 10 people over and over and over and over and over again, the expected value would be 0, right? Assuming everybody has an equal chance of winning. Now, you might say, well, some people know the sport better, right? Some people just pick based upon the mascot. Who knows? But in theory, if you assume everybody has an equal probability of winning, which a lot of times that's the case, then the expected value would be 0 for this kind of a game.